So, welcome to Alejandra's session. I think she can welcome you all to your session, and then we haven't figured out exactly who is introducing who. So I'll introduce Alejandra. You can introduce everybody else.
Yes, I can.
And,
Thank you.
And take it over.
Given that I cherry-picked them, I will be able to introduce them. So thank you, David. Thank you to the organizers for having this session in such a wonderful and fashionable topic of black holes. So I'll start the theme by talking about some recent work that was related to black hole physics, and all the details I'm going to, since we have a short time, all the details of what you want to see and don't want to see are in this paper, which is in collaboration with this great team of collaborators, Luis Apolo, Susana Ventalla, and Diego Lisca. There was some period of time that we were all in Amsterdam when this project started. Starting in October, all four of us are going to be in different places, but please, these are the most junior people in the collaboration. So keep an eye on them because they're really fantastic and behind the work that is going on. So what is the topic? So as we know, when we talk about black hole entropy and trying to describe it microscopically, modular forms have played a really pivotal role in understanding the microstates. The examples, the very precise and sharp examples that we have in string theory always involve modular forms. So what I want to do today is I want to revisit that success that we've had in understanding black hole entropy from modular forms, and I want to tie it with other aspects of ADS-CFT. So there's a sense in which what we're doing is kind of going back and taking a step. And it's like, what have we learned? So the context of what we're going to be doing is basically I'll be looking at supersymmetric black holes that are also extremal. This is something that I have to say nowadays, both BPS and extremal. And I'll be looking at examples in 4 and 5D on-gauge supergravity. And in these cases, so the black hole entropy, it has a leading part, which is the area law, the very famous area law. But for these type of BPS and extremal black holes, you can also extract what's called this logarithmic correction, this log A correction, and there's a coefficient up here. And these are some of the people that were involved in doing these computations. And I'm not going to spoil it for you, this is well known. The leading part and the subleading part match beautifully with the microscopics. And these are things that we brag about as string theorists. Now, what I want to do is basically revisit what did we learn by doing this matching, okay? And in particular, what did we learn by understanding, by basically matching this logarithmic correction? What new information did you learn about the microscopic theory, okay? That's basically the motivation behind this work. So let's start understanding what goes into the gravitational derivation. So you have a black hole. Let's say that it has some electric and magnetic charge, Q and P. And what you would usually do is compute a gravitational path integral for some fixed value of Q and P. Now, this path integral is usually solved by a saddle point. And so there will be a tree-level contribution, and then there will be a one-loop contribution. And this saddle point is basically something that you can trust reliably in the scaling regime. So this will be quite important. The charges of the solution have to be very big, and in a certain, here I'm putting it with appropriate units, and then the area of the black hole, the saddle point you trusted when the area of the black hole is very big, and in this regime basically then you can extract both the leading part and the subleading correction. Now from the microscopic, and this logarithmic correction has two contributions from the point of view of this path integral. There's a local contribution that comes directly from this one loop correction, and then there's zero modes that usually come from isometries that the background has. Now, these black holes are usually the near horizon geometry is something that is of the form ADS2 times a sphere, being very schematic. And then we'll think of them, for the configurations that we'll look at, they have an uplift to ADS3 times a different sphere. And this is where the modular forms come in. Because you're going to be doing secretly ADS3 CFT2, where in the CFT2, the counting formula is usually a modular form. And so we'll be looking at things that are supersymmetric, so you're counting BPS states, and usually it's the trace of -1 to the f with appropriate parameters. And the name of the game is basically to extract this Fourier coefficient here, okay? Which universally has an exponential growth with corrections. And in the CFT, basically from this point of modular forms, the parameters here, this n and l, usually go into this discriminant, and this delta 0 is basically the central charge here, minus c over 24. Now, a lot of hard work goes into implementing this specific scaling in order to extract basically the corrections. So you want to basically not just have the leading exponential corrections, but the leading correction, but also the exponential ones. And so this is the part that is not trivial about this exercise. And basically after doing this careful analysis, order by order, you can start seeing that the log of the number of states is basically the black hole entropy, which is our dream, right? To understand the black hole microstates. Now, what I'm going to be focusing on is basically what controls these corrections from the microscopic point of view, okay? So the majority of this presentation is about this. And in particular, something that we wanted to understand, if like when you match it to the black hole, was the matching just something that came just from symmetries, or if there's something actually dynamical happening here? Okay, so how should you interpret the fact that you successfully matched this? If it was guaranteed, or if it is actually a new point in the whole discussion. So what I'll do, I'm basically going to tell you a little bit about how we did this, and I'm pretty sure I'm going to run short of time. So I'll try to go through this quickly, but that's where you can read the paper. We have a lot of information. I'm not going to touch the second topic of symmetric product orbifolds and exponential lifts. There's extra slides at the end of the PDF if you want to look at it, and you're also welcome to read the paper, but this is only 25 minutes, and we have to speed up. But I wanted to focus more on the specific examples, on the specific BPS black holes that we looked at, and revisiting what it meant to match those logarithmic corrections. Okay? Very good. So let's get started with this asymptotic expansion. So the object that we have, this index that we're going to be computed, is basically controlled by what's known in mathematics as a weak Jacobi form that has a lot of nice modular properties. It also has elliptic properties. And these properties, basically, the elliptic one in particular, tells us like, it's nice to organize this thing in terms of this discriminant. And usually when you look at the states that contribute to the sum, in terms of this discriminant, there's basically two types of states, which is jargon that I'm going to be using a lot throughout the talk. So there's things that we call light states, or polar states, where delta is negative, and then heavy states that have delta that is positive. Okay, so think about like if you want a gravity language, this will be perturbative states in the gravitational context. These will be black hole type configurations. Okay? And then the most polar state is what I'm calling here delta 0. Okay, that's the notation. Now, for a Jacobi form, it's also very well known in mathematics for many years, is that if you wanted to know its Fourier coefficients, there's an exact formula. It's called the Rademacher expansion. So what is this formula? It looks scary. So basically here I'm trying to understand the number of states of the non-polar configurations. And it's basically controlled by some known functions. So everything here is just an explicit function. And then the input, the only thing that you needed that was special to your example, is basically what the light states are. So this is a version of like where light states basically control the degeneracies of heavy states. It's a consequence of the S transform for these modular objects. Okay? And so you would say, great, Alejandra, here you have it. If you give me a Jacobi form, you can know what the Fourier coefficients are exactly and precisely. And it's just a math problem of like then seeing like, oh, where does the log correction come from? And you're done. However, I'm not going to, and in particular, for instance, the exponential growth that you get, it comes from this Bessel function. And so this is the part that we always call like the Cardy-like formula. It just comes from that contribution in that sum. That's a very universal piece. That's why this exponential growth really doesn't depend much on anything else that you had in there. Great. So the homework was done for me, apparently. But actually, no, I'm not going to use this formula. It's elegant, it's beautiful, but it's actually not useful for the gravitational applications that I wanted. And what is basically the problem? So there's this parameter here, the index, which is basically the central charge. And one thing that black holes do is that they treat this parameter as a continuous parameter. Okay? And in particular, it will be one of the parameters that from the black hole point of view gets scaled. And so I want to treat it as a continuous variable. I am extremely intimidated by taking a range and a sum to be something continuous. I get nervous about that. It's not my forte. And so, and this will actually, as we'll see, will affect how you think about these logarithmic corrections. So I will make comparisons when appropriate with the Rademacher expansion, but it's not useful because I really need to think of t not as an integer, but I need to think of it as a real variable when I want to compare with black hole physics. And so we'll do a more mediocre job. So similar to what Jan was doing in the morning. No, he was doing a great job, but this is my version of introducing a density of states. And so basically, because as we learned from the morning, you want to have this coarse understanding of what's happening and then connect it to the exact microscopics of the CFT. So we'll introduce a density of states. We'll not think about these things being continuous, and then try to extract the information from that point of view. And this is what we call basically the crossing kernels. And in the context of the crossing kernels, then you use basically just the S transform of the modular form, and this allows you to write what the density of states of heavy particles is in terms of light particles. And here, if you compare it with the exact density of states, this usually is going to match, plus some exponentially suppressed corrections. So that was our approach. Now, the other thing that we need to do is to incorporate gravity. So how do we tell this modular form that is supposed to be matching something gravitational? So this comes in basically constraining what the light states are. This is where gravity comes in. Okay, so you have to tell me something about this light spectrum. And something that was done very nicely back in 2014 is that in a CFT, the first indicator that you have that the CFT has a gravitational feature comes in demanding what we call the sparseness condition on the light spectrum. So the number of light states cannot extend beyond Hagendorn. And also, very importantly here, you can't have this prefactor, it's actually 2 pi. You can't have any other type of prefactor in front of it, okay? And this sparseness condition, basically what it did, it allowed you to claim that the density of states was exponential in a regime of validity that is much bigger than the usual, what people call the Carty regime. Okay, so we want to incorporate this as a condition in our modular forms. So okay, so we're using crossing kernels, and we're combining it with the sparseness criteria, and the outcome of this, there's a lot that I'm skipping over here, but we basically found that there were 2 regimes. There's a universal regime where you can get an exponential growth of states, where basically delta and delta zero are comparable, and this is basically how the leading part and the corrections look like, where this part here is basically the ground state degeneracy. And then there's a non-universal regime that will also be important for our black holes, where actually delta zero is much bigger than delta. And then here, there's many examples. It's not, I can't write one formula that fits all, so I put here one example just to illustrate how more complicated the asymptotic formulas look like, and this here is such an example. But okay, so that's all I have to say about the crossing kernels, and I'm pretty sure I'm doing terrible in time. Okay-ish. Fine. Okay. So let's now revisit, let's go into black holes, because that's the name of this session, and we actually want to understand black hole physics. So again, what I'm going to do, I'm going to give you a summary of like what happened gravitationally, and then we'll basically contrast that with this microscopic derivation, and then understand what did we learn about the microscopic theory, what were the ingredients that were needed in each case. So the first example is quarter BPS black holes in n equal 4, d equal 4 on gauge supergravity. And so there, these are like a dionic black hole, so you have an electric and a magnetic charge. Well, there's many of them. I'm being a little bit brief with the notation. But basically, the charges all scale uniformly in this example. And then the area law is given by this beautiful formula here, in terms of this quartic invariant in supergravity, so q squared p squared minus that. And then the logarithmic corrections were computed. So this A gravity has contributions that are local. They depend on the number of vector multiplets. They depend on the number of hypermultiplets. They depend on the number of supersymmetry. If n is equal to 4, then you always have this constraint between the number of vectors and hypers, and so then this number is -1. And then you have zero modes that are coming from the isometries, killing vectors from the ADS2 times S2, and then fermionic zero modes, and then that answer is 1. And then the total -1 plus 1 is 0. So there's no logarithmic correction for black holes in n equal 4. What happens from the microscopic point of view? So, okay, so the counting formula is it's a modular form. It has a big fancy name. It's called the Gusa-Kuss form. But in any case, we can talk about it in our language. You translate, so the parameters I was calling T, N, delta 0, all of these things have translations to the parameters of the modular form. And you can see then that what I'm calling here this regime, it gets translated to a regime where delta and delta naught are of the same order. Okay, that's what the scaling regime implies in the CFT. And this is the universal regime in the CFT. So the only thing that you needed to know in the CFT to match, like the only thing that can control this logarithmic correction here, and I wrote it here in a suggestive way that it comes from the data of this Gusa-Kuss form, is this number that is basically the number of Ramon ground states. That's the only thing that controls the log correction from the point of view of the CFT. So from this point of view, from the gravitational point of view, I needed to know quite a bit about the spectrum and stuff. From the point of view of the microscopics, the only thing that it could enter in this universal regime was the number of ground states. Okay, now let's look at a more different example. So let's just go up one in dimension. So the same black hole, but uplifted. So this is the BMPV solution. And in this case, you also have electric and magnetic charges, and you also have rotation. And then the formula, the area law, looks like this. And then here, the thing that is very interesting is that if you're in 5 dimensions, there's no local contributions. Okay, so an odd number of dimensions, you never will have a local contribution. And then everything that you have here comes from the zero modes. Okay, so here I wrote the answer in the case where this black hole is embedded in type 2b on K3 times S1. The microscopic derivation. So the relevant counting formula is the generating function for a symmetric product orbifold. And then here I wrote how you translate each parameter of the CFT to parameters of the black hole. And the thing that is really interesting is that now I'm not in the universal regime. I'm in a non-universal regime. And that means in particular that I need to know much more about what the modular form is controlled by. It's no longer something where I just say that the ground state is contributing. And so here I wrote basically the intermediate step of what goes into that information. So this is how the coefficient behaves. And this is what we needed to know. The light spectrum is something that you can figure out like from the modular form. You can also figure it out from the supergravity point of view. And this is the data that goes in. The precise numbers, so again, you have the Ramon ground states, 2 of them contributing. But here you have this weight that is basically controlled by the H11 number of K3. But all of this basically confabulates to actually give you the same number. But what I want to be emphatic here is that in this case, this answer seemed pretty trivial, just controlled by symmetries. This side, I actually needed to know the behavior of a whole tower of states and their asymptotic growth in order to get the right answer. Okay? Now, my favorite example is this one. This is the example that gave us I still wrote, sorry, I have a typo there. It's not BMPV. I'm back in 4D. Apologies for that. This is going to be, again, a black hole that has electric and magnetic charges in 4D. But I reduced it to n equal 2. Okay? So in this case, again, charges are scaled uniformly, and the area law has this form. TheCijk is basically intersection numbers. These black holes, from a higher dimensional point of view, they have a Calabi-Yau floating around, but it doesn't matter. But this is basically the area law, and again, people computed the logarithmic corrections. And in this case, I just have to put that n is equal to 2, because in n equal 2 supergravity, I can have different number of vectors and hypers. And then this is the basically the answer for what a gravitational is. Okay, so now I move to the microscopic derivation. So depending on your taste, you can think of this in terms of MSW, OSV. Do not ask me what OSV is. I still, although reading back on all those papers, people that are old enough in the audience will understand why I'm making a joke about this. Any case, this is not like, so there's some understanding of what this modular form is, but it's something that we don't have exact access. But from our perspective, I don't need to know exactly the modular form. I need to have a handle on the light states. That's all I need to know if I want to understand what the light part of the spectrum is. And this again, that's also why this is quite interesting. These black holes again land in the non-universal regime. 5 minutes, great. So delta zero is also much bigger than delta. It's basically because delta zero is this intersection of these three P's, and delta is just this Q naught. So if all of them scale uniformly, one of them goes like lambda cubed, and the other one goes just like lambda. And so the hard work was basically having a grasp on what these light spectrums did. This is beautifully what you get. There's all sorts of data here. But the thing that you can see at the end in terms of the logarithmic correction is that when you put all of these things together, so here, for instance, there's a weight that is controlling the answer, which is given by the Euler number of the Calabi-Yau, and that's where you see that you get this combination of NH minus NV. So all of the things here fit quite nicely, and you get a perfect match, and you're like, yay, it worked. But there's something also that is really interesting in this example, is that actually when you look at from the mathematics point of view of trying to extract information in the scaling regime, notice that here my exponential growth, I'm only bragging that I'm matching the logarithmic correction. This is a case where quantum corrections actually overcome your usual Carty-like formula. So from the modular form point of view, the area law is no longer the dominant contribution. And this is very clear from the perspective, if you do the path integral from the perspective of ADS3. From ADS2, gravitationally, it's not obvious, but the knowledge that was known about what are the objects that this is counting at weak coupling did also indicate that there should be non-perturbative contributions here. So this is an example where the log correction is matching, but you actually, your path integral is not, the saddle point is not just controlled by the black hole. The quantum effects around the black hole are overwhelmingly it if you are in this scaling regime. So let me now conclude in this last couple of minutes. So basically, what we were trying to do is trying to have an understanding when you're doing this gravitational computations on how they basically match, or what does it mean for you to match them from this microscopic perspective. And I think something that is really interesting to think about in this context is that maybe in one side of the duality, the answers are very simple, are dictated by very few things, but usually in these three examples that I showed, I wanted to convey that it doesn't go both ways. So either things were simple on the gravitational side and then very complicated in the CFT side, or vice versa. The answers are very simple, very universal in the CFT side, but then what comes in the gravitational side to make them match is not quite simple. And I think this also illustrates a way of how can you think about CFT observables when you're trying to treat n as a continuous parameter. So how do you actually extract data, not for specific values of n, but actually thinking of it as something that you're allowed to tune. And that was part of what we were doing here. But there's other observables that you can do this. And then to end, I did want to end with an important outlook that comes to trying to do this in ADS4. So there's also computations of deriving this microscopic entropy from the point of view of ADS4. And this is where supersymmetric black holes in ADS4 actually have way more interesting behavior of what this A gravity is. And it depends, it matters a lot if you are on ADS4 times S7 versus if you're just in ADS4 by itself. And so one interesting open question here is that as these numbers are matched, so for instance for these examples here, when you are in ADS4 times S7, they do match the dual CFT. It's not really clear what would happen, for instance, if you just have a lower dimensional theory, then these coefficients are actually non-trivial functions, and it will be interesting to understand what it happens, how do I think about like either these corrections or these corrections, basically how are you extracting them from an appropriate index in a higher dimensional context. So I think a very interesting future question is basically understanding the nature of that in not just ADS3 CFT2, but going higher. And with that, I'll end. I had at 0, right?
Questions?
Exactly at 25.
Going back to the BMPV story, I haven't been really following it closely, but I remember there was some discussion about the zero modes on the gravity side.
There's different, nowadays there's different types of logarithmic corrections that you can look at.
Oh, okay, so this is different.
Yeah, so those are log T corrections. These are log A corrections. So this is a correction to just the extremal solution and supersymmetric ones.
That probably needs to go beyond the externality.
Yeah, because it's a different, it also has a different origin. It also, there's a way, it also comes from a one loop determinant, but it's not the same correction here. So yeah, so the difference is that here I'm computing log of A at 0 temperature. They're trying to figure out what is log of T when T is very small.
Okay.
And that's mostly zero modes that are contributing to the, it's understanding very, very carefully what are the important zero modes when you go a little bit away from extremality.
Can you explain a bit about the crossing kernel? Is this related to the modular S matrix or something different?
It's very much inspired by that. So basically, yeah, I kind of like threw all of, Diego will kill me because this is his favorite method. So this is basically, so you write this as a continuous number, continuous density, and then you're basically just trying to understand what are the constraints on that density based on just doing an S transform.
Okay, but maybe even more basic question. You put trace with -1 to F insertion here.
Yeah. But
that's not what you normally think of as an entropy. But so
no, exactly, good. So that you might worry that, yeah, so I'm using the word density of states a little bit, I'm abusing terminology here. So it's just a distribution, if you want. So this does not require positivity. So for instance, if I wanted to do something like a Tauberian analysis, then it would be very important that these coefficients are positive. But from the point of view of just thinking of this, if you want, let me not say density, let me just say distribution.
Okay.
They don't have to be positive for the analysis to go through. These steps don't assume positivity. So they don't have to strictly be like a density.
Right.
Yeah. So they're just delta function supported distribution. Sure.
Could you explain what you meant by the non-universal regime?
So it's a regime, like usually in, well, if you're very familiar with ADS3 and like the BTC black hole, you tend to think of the BTC black hole as something as dominating the ensemble when the energies are very comparable with the central charge. And that's usually what happens. The non-universal regime, which occurs when you basically go down to ADS2, is that not always, but it can happen, and it depends a lot on the way that the dictionary is set up. It's a case where the central charge is much bigger than the energy. So that's what happened in 2 of my examples. So for the BMPV black hole, you're counting states that have C much bigger than E, where C is Q1 times Q5, and E is the momenta in the D1, D5P. In the MSW case, it was like C was the intersections of three charges, and Q was just the energy. And that's what it means. You're basically trying to explore the CFT. You're trying to see if there's something universal about their density of states when the central charge is much bigger than the energy. Both of them are pretty big, so everything is scaling with G Newton, but there is a bigger hierarchy on the central charge compared to the energy. So that's, and we call it non-universal because the corrections are not, I can't write, like in the other case, if central charge was comparable to energy, I just had one very simple formula. It's basically, it looks like the Cardy formula, where you have to acknowledge that in supersymmetric cases, you have degenerate ground states. But in the non-universal case, I really needed data of the CFT to be able to access that correction.
Okay, it's time to move on. So let's thank Alejandra again.